sort of priority use cases. So in the final session today, we're going to be looking at some of those opportunities, and as well as the first session tomorrow. We tried to interject, this morning was primarily technology, science and technology and engineering, technical things. We want to look at these use cases and see what people have at front of mind, the potential applications. And then tomorrow, when you come back, hopefully we're going to delve into the database and what we're actually going to be created. So that was sort of the layout. So with no further ado, because we're running a little late, I'm going to introduce Albert Kottke of Pacific Gas and Electric, and he's going to give us some perspectives on energy system use cases from PG&E. So Albert, it's all yours.
All right, I wanted to thank Dave and the other organizers for inviting me to this. And I'm going to talk about something totally different in a totally different perspective. So to jump in, we're going to talk about risk attitude. It's something we haven't talked about at all today. So risk is how we measure impact of earthquakes to our infrastructure at PG&E, and all utilities will use the same process. And risk attitude describes the fact that not all losses are the same. Small losses may not be as impactful to big losses if you are risk adverse. So at PG&E, we quantify the risk using a multi-attribute risk score that considers safety, so that's injury and loss of life, financial, what's the economic impact of losing an asset, and then reliability, what's the impact to our customers. In risk-adverse scaling, large consequences have an inflated risk score. So if we see a lot of loss over a large region, that's going to be a riskier event with a higher score than maybe a small event. So from an earthquake perspective, a small earthquake is not as important as a big earthquake, and not just because more things are damaged, but more things are damaged simultaneously, and the scaling is this nonlinear function. And the risk-adverse scaling, it impacts how we perceive earthquake threat when we look at future modeling. And this scaling is super important when we look at regional performance. So if we look at PG&E assets, PG&E maintains a wide range of assets. We have a nuclear plant that you might know of. We've got about 166 hydroelectric dams, 106 powerhouse or generators at 67 powerhouses, I think. 20,000 miles of electric transmission lines. Interestingly, the circumference of the Earth is about 26,000 miles. If you add our electric transmission and gas transmission together, it would go around the Earth once, which I was pretty impressed with. What I'm showing on the figure there is those are substations, gas transmission, and gas distribution lines in the Bay Area. So the density of customers and assets in the Bay Area makes it for a really important area for identifying risk. And it's not risk of a single asset, but it's all of these assets together that's really important. So when we start thinking about how we think about these, we can't just think of one. We have to think about the ground motion over this entire area and how those are all going to play and interact together. So how do we do our risk assessment? A few years ago, we just had a handful of motions that we were propagating through our risk tools. Since then, we've developed a more sophisticated approach where we're using suites of scenarios. So first, we develop a regional probabilistic hazard assessment, and that's going to quantify the seismic hazard over a grid of points. That can be the USGS hazard. We have a PG&E specific hazard model as well, and we're always working towards refining that. From that hazard model, we're going to select sources that are hazard significant and that are going to be really contributing to the risk. From that, we now want to downsample our hazard into a number of scenarios that we can propagate through our asset models to come up with risk assessments. And right now we're finding about 300 scenarios can both capture the hazard over the area and do that in a realistic way, but also be manageable enough that we can do risk assessment with afterwards. So what's really important about these scenarios is they capture the spatial and intensity measure correlation. So our PGV, our PGA, our spectral acceleration at a number of different periods are all have realistic correlations. But then also spatially over our area, we're seeing pockets of high shaking and weak shaking. When we add all of those scenarios together, at any point within the region, those scenarios associated with the rate that we define for them capture the hazard curve. So now we're basically breaking up a hazard curve at each point to 300 discrete intervals. And then we adjust those for site-specific conditions with VS30 maps, so we have realistic shaking at each point to a site condition. Then we can take these maps along with their rates, and we can apply them to secondary hazards to look at liquefaction and landslide threats. But we can also look at how our assets perform, look at our substations, our transmission lines, our buildings. We can then look at the performance, look at the different consequences in terms of safety, reliability, and financial, and we can come up with annualized rates or annualized losses. Sorry, we have our rates, we can come up with annualized losses by adding those all together and multiplying by our rates. And that'll give us a risk score. So we've done this. This one example is just using our stock of buildings within the Bay Area. So we own about 170 or 760 buildings. I think we have 140 within what we call the Bay Area. The red line there and the figure on the left represents the USGS hazard curves. The blue points are just our scenarios. And you can see in some cases our scenarios are overestimating the hazard, in some cases they're underestimating the hazard. We can certainly improve this process. If we just compare the blue and green bars shown in the figures, one is using the hazard curve explicitly and the other is using the scenarios. And we see that our risk scores are essentially the same from these two different processes. That means that our 300 scenarios are doing a good job of capturing the hazard for these buildings. The orange is if we, for every scenario, we scale the score by our nonlinear scaling factor. So we use that risk-averse process to increase our score when we have a lot of simultaneous damage. And what that means, if we just look at total risk, we essentially have twice as much risk if we consider simultaneous damage than if we don't. And this is just using 140 buildings in the Bay Area. So what is happening here is the earthquake scenario effects are more pronounced because buildings are clustered together. So if one building is damaged, that means that other buildings in that cluster are going to also be damaged. And that's going to add together, and that score is going to inflate it. That nonlinear function is going to inflate it. As we increase in the number of assets considered, we're going to see a greater importance to the correlation, and it's going to further inflate the risk scores. This is just PG&E that we're talking about, but when we think about society and how much damage is going to occur to this region due to ground shaking, this sense of scaling of risk, I think it's, why do we scale risk? Because we think of really big events as being really costly and a lot to recover from. So as we add events, or we add inventory, we're going to see more scaling, we're going to see more damage, bigger events are going to be even more costly. And so that's really think that correlation of ground motion intensity spatially is a really key aspect when we think about how do we think about risk. So these scenarios that I'm talking about, there's some advantages to them. You know, each scenario is associated with a rate of occurrence, and it's consistent with the hazard. So that means the ground shaking intensity is constrained by the hazard, and we've done a really, I think, robust job of characterizing hazard within the region. And as we change that hazard, we can accommodate those changes to hazard with new maps. You know, we're only using a limited number of maps. We use about 300 or so. I think that's few enough that we can, non-technical stakeholders can understand sort of what that means. You can look at a low return period event, or you can look at a high return period event, and there's a tactile nature of having a limited number of sets. And we can also talk about the range of performance from those individuals. And the other thing that's really important about these scenarios is it's capturing a realistic spatial and intensity measure correlation. And that spatial correlation is really important when we look at distributed infrastructure or large societal impacts. So here's an example of what that variation in ground shaking looks like over the bay. But there are some clear disadvantages to the scenario approach that we've been using. The current approach is based off of ergodic ground motion models and ergodic correlation models. So it's capturing typical spatial correlation, but it's not capturing Bay Area correlation. So the hazard that we're adjusting to is again on ergodic models. As we do this again in the future, we're going to be using non-ergodic hazard models. This Bayesian correlation doesn't really consider the fault and velocity specific, or velocity structure specific to the Bay Area. So we need to go through and improve that so we can do a better job of understanding what the ground motion looks like spatially. The number of maps influences the realism of the selected events. So as the number of maps decrease, the event term or average strength of those events has to become more uniform. And so we see less site-to-site variability and more event term, and it balances from the event term. So currently we're using about 280, and that's capturing return periods between 100 and 10,000 years pretty well. And this process approximates the hazard calculation, so it's sort of done outside of the hazard integral. And I think it's approximate, so that's a disadvantage, but it's really, you can't put this into the hazard integral. There's too much. The correlation structure is too large to do that. So that's our risk assessments. Let's talk about simulations. So first of all, PG&E has been supporting improvement in numerical simulations for, I guess, coming up on 30 years. We initially started supporting SCEC back in 1994 after Northridge, and we continue supporting them today. We also work on project-specific topics, both at universities and national laboratories. PG&E supported projects have used simulations. A series of NGA projects we have supported, and they've incrementally used more and more simulations. And NGAOS 3, which actually there is a meeting going on today on NGAOS 3, will be using more simulations than ever before, and which is really exciting. We had the Fault Displacement Hazard Initiative that looked at some physics-based modeling of fault displacement. And at Diablo Canyon, we've used simulations for ground motion modeling as well. And why have we been investing in simulations? And that's because we really feel like simulations have an important role to play in understanding earthquake ground motions. But I think what's really important is that we leverage both simulations and observations to better quantify seismic risk. We can't use one tool or the other, or we can't use observation or simulation alone, but we need to use those together. So my vision for how do we use simulations in the near future is somewhere within this spectrum. There is some people that just want to disregard recordings for these large magnitude events, saying, well, we haven't recorded anything like that, we're going to extrapolate to these large magnitude events at small distances on simulations alone. And I think that's the wrong approach. On the other side, some people don't trust simulations. They really rely on observed ground motions, and I think that we can't do that either. Instead, we have to figure out how we're going to basically use simulations and observations together and do it in a sophisticated way. And I think that maybe NGAOS 2, we are at limited use of simulations, and I think we're going to be at equal use of simulations at NGAOS 3 or maybe soon afterwards. If that's sort of on ground motions, if we think about risk calculations, here I think that we can think about risk calculations and use simulations as part of that process. And we have to do so in an incremental fashion rather than replacing the process. So SCEC is going through this cybershake effort of computing hazard using simulations. I think it's a great practice. I think we're learning a lot from that, and we can pull a lot from all of those simulations, but I'm not ready to take those hazard products right away. But we have to do that to test what we know. So I'm really looking at incrementally improving ground motion modeling. So develop ground motion models using a combination of observed and simulated ground motions. This requires increased sophistication of our ground motion models to capture spatial complexities. So we're talking about using Gaussian processes or machine learning based spatial models to try and look at what are the source to path effects that are not being captured, and now develop ways to capture those. Once we have these new sophisticated spatial models, we need to put those back into seismic hazard analyses to compute hazard. The hazard analysis process, we go through an intense scrutiny on characterization of source and its uncertainties, ground motion and its uncertainties, and I don't think that we're ready to replace that yet, but rather inform it through the simulation environments. The scenarios will also help fill voids in earthquake catalogs and large magnitude events along the predominant faults in the Bay Area, for example. I'm interested in using simulations to generate scenarios, but those scenarios should be constrained by the ground motion and rates consistent with the hazard. So we shouldn't see ground motion intensities coming out of scenarios that are totally inconsistent with our hazard curves. I also think that simulations can help identify specific features of faults. For example, creep was talked about by Rob Graves, and that's an important aspect to Bay Area faults. And I think it's more than just parameterizing the problem or looking at the sensitivity, because we can do that already. We can adjust slip or maximum magnitude of these faults, but the real question is, what can simulations tell us about the physics and help us figure out what's going on so we have a better idea rather than saying, well, what's the sensitivity of this problem? Fault-specific geometries and roughness can be looked at, and then also linking of ruptures between faults in the region. Some of the challenges in using simulations, I think we spent a lot of today talking about all of the complexity from both the rupture generation to the wave propagation to the near surface behavior. And that's all buried in there, and there's decisions that have to be made and improvements in modeling that are needed. We have limited information on our velocity model, and that limits the usable frequency range. We have high frequency calculation requires excessive calculation time and limits the ability to sample different conditions. And previous efforts have really focused on specific or deterministic realizations. What's a magnitude 7 on the Hayward? And I'm going to generate a suite of ground motions for that. But if we think about what the future magnitude 7 on the Hayward might be, it's probably going to be none of those. So we really have to think about a probabilistic way. And so we have to go back to hazard. And for a specific simulation, we have no sense of the rate of occurrence. So if we don't have a rate of occurrence, then we can't think about risk. And so we always need to go back to that. So this is an idea that I have to look at generating hazard-consistent simulations. So first, take a typical ground motion model and hazard model to develop a non-ergodic ground motion models that are going to capture the spatial variation in hard rock and site-specific conditions and create a map of hazard. From that, we can then generate a suite of simulations over that region for sources that are risk consistent. We would compute this at the hard rock and maybe use a cybershake-like process to come up with a huge suite of realizations. The sources that we use in those realizations could be informed from hazard or maybe just based off of simulators like EQSim. And we would compute over only the deterministic period range. From that set of millions or so of simulations, we could reduce them down to a selected number, selecting a rate of occurrence that captures the hazard, and choose the events that, combined with that rate of occurrence, match the target hazard over the return period range. This is very similar to the process that we use when we generate these scenarios of maps. But we would be doing it over the deterministic period range. We could then go back, adding higher frequencies and adjusting for side effects by using the kinematic slip realizations of the selected scenarios, so we know that the long periods would fit already, and we would just have to figure out how to stochastically match our short period response to the short period hazard. And that forward modeling is more numerically time consuming, but it can include soil nonlinearity. And then the complete frequency range can be filled in by the stochastic motion if necessary. And so the purpose of this is basically to try and figure out how to leverage huge sets of scenarios with also more sophisticated sets of scenarios to come up with a suite of simulated motions that, again, would be hazard consistent. So just some quick conclusions. Improving ground motion models really is going to require both simulations and recordings. Construction of seismic hazard models requires model building decisions, and those shouldn't be really replaced by simulations. And so in the near future, the mechanisms that we define Earth ground motion hazard aren't really going to change, but the components of them may. Consideration for spatial correlation is critical for risk assessment over regions. It's captured by hazard consistent scenarios. The risk adverse attitude causes scaling of this and really increases the hazard score. And that increases more as more assets are considered. And so if we look at PG&E versus all of the society in the area, those are going to be different scores. Simulations can provide unique information on regional spatial trends on large magnitude events, which can be incorporated in ground motion models for hazard calculations. And we need to use hazard to inform simulations. And so it would provide constraints on the simulations in terms of the ground motion intensity, but also might provide a mechanism to define the rate of occurrence for a collection of events. And with that, I don't think I have questions now, but I don't know who made this cross-section. I found it on the internet when I was Googling things, and it's gorgeous. So I just wanted to put it back up there.
It's like it's from the 40s.
Yeah.